Let us now do superposition theorem. What superposition theorem tells us is that if we have a cell like this, we have one battery and the second battery, and we are told to calculate the voltages and currents across each resistor. On first attempt, let's short one battery and work with one battery. This is what I've done here. On second attempt, let's short the battery that we didn't short and work with the battery that we shorted. That's what I've done there. How does this helps us? Like here, you now see that this is a series parallel combination. So we can calculate the total resistance of this parallel circuit and add it to that resistance which is in series. After that, we will be able to calculate the total current of the circuit. We know that a total current of the circuit is the same as the current that is flowing through R1. So if we know the current across R1, it's easy for us to get the volt drop across R1. After we got that volt drop across R1, it's easy now for us to get the volt drop across this parallel circuit. We know that if we get the voltage across the parallel circuit, a voltage that is here and that is here is the same. So if we know the voltage here and here, we can calculate the current here and here. So after doing all of that, we then come to this circuit, we do the very same thing. It should be noted that the currents that we get here and the voltages that we get here are not for this circuit. They are for specific for this circuit and this circuit, but we can use those currents to get the currents across here, and we can use also the voltages to get the volt drops across this circuit or on this circuit. So now let us just do what I have just explained. So on this paper, I've just drawn this circuit. So B2 is shorted, B1 is shorted. Now let's work with this circuit and calculate the currents and voltages. So we said we will first calculate the total resistance of this parallel circuit, which will be 4 times 2 divided by 4 plus 2. And this becomes, what does the calculator say? The calculator knows math and I trust it. So 4 plus 2. The calculator says this is 4 over 3, which is the same as 1 over 3 ohms. So if we want the total resistance of the circuit, we add R1, which is the resistor in series, with R parallel. So R1 is 8 ohms and R parallel is 1333. So this tends to be 9,33 ohms. So we got the total resistance. Remember, we said we will use the total resistance to calculate the total current of the circuit. The total current of the circuit will be calculated by taking the voltage across B1 and divide it with the total resistance. So this means that we have 56 divided by 9,333. So what do we get? Our total current tends to be, if we say 56 divided by 9,333, we get, if we're rounding off to 3 decimal places, then this does not change this 0 to 1. So this is the same as 6 amperes. So we now know that the current across R1 is 6 amperes, but we don't know the current across these resistors. Let us use the current across R1 to get the volt drop across R1. So the volt drop across R1 will be current times voltage across R1. So we'll use the total current. The total current is 6 times 8. So if we multiply there by 8, we get 48. So, sorry, well, yes, we get 48. So our voltage drop across VR1 is 48 volts. So let us use this volt drop to calculate. Let us use this volt drop to calculate the volt drop across the parallel. VB1 we know that must be equal to the sum of the voltage across R1 plus the voltage across the parallel. So the voltage across the parallel will then be VB1 minus VR1. I hope you understand where is this coming from. We just flip these things around, then we transpose VR1 to this side and VR1 becomes negative. So VB1 is 56 and VR1 we got it here, it's 48. So if we say 56 minus 48, what do we get? The calculator says it's 8. So therefore the volt drop across that parallel circuit is 8. So we know that here we have 8 volts and here we have 8 volts. Since this is a parallel, here we've got 48 volts here. So we know everything now across R1. The only thing that is left for us to calculate is the current here and there. Now that we know the voltage drop across these resistors, we can calculate the current across R2, and it will be 8 divided by what is the resistance is 4, and this tends to be 2 amperes. We can just take this and subtract it there to get the total current, but let's check if it balances. If we don't do this, we still take 8 and divide it to 2. What do we get? We get 4 amperes. So if you add this current and this current, you get that current. So what's the current across R2? We saw that the current across R2 is 2 amperes and the current across R3 is 4 amperes. So the sum of this gives us that. Then we know that we are on the right track. Now let us come to this circuit. To this circuit, again, we start by calculating the total resistance across the parallel circuit, which will be 8 times 4 divided by 8 plus 4. And this tends to be, let's press it on the calculator, times 4 divided by 8 plus 4. And the calculator says it's 2,667 ohms. Now we want the total resistance. We still use that same formula, but now our R that is in series is R3 plus R parallel. This would be 2 plus 2,667. Then the total resistance for this circuit is 4,667. If I'm fast, you just pause the video, go back and listen to what I've said. I don't want this video to be very long. That is why I'm very fast. So after getting the total resistance, we calculate the total current of the circuit, which we know that it will be the current across R3, and that total current of the circuit will be calculated by 14 divided by 4,667, and it turns out to be 14 divided by 4,667 is equal to, that's almost 3. That's 3 amps actually, because if you're rounding off to 3 decimal place, this 7 will change this 9 to 10. You carry 1, you keep changing, then you add 1 there. So we know the total current, and we said now this current, which is 3 amps, is the current that is across this resistor. So we're going to use that current to calculate the volt drop across R3, and we will say 3 times 2, because voltage is the product of the current and the resistance. So this becomes 6 volts. So we know that the voltage there again is 6 volts. We can use this voltage and this voltage to calculate the volt drop across the parallel circuit, which is going to be 14 minus, I'm deriving formulas the same way that I did on this side. So if you lost here, just come back on this side. So it's going to be 14 minus 6. So if we say 14 minus 6, what do we get? We get 8. So the voltage across the parallel circuit is 8. So we know that the voltage here is 8 volts and also 8 volts there. So now we can use these voltages to calculate the current across R1. It will be 8 because that's 8 volts divided by 8 ohms. That would be 1 amperes. And the current across R2 would be 8 volts divided by 4 ohms, which is 2 amperes. So across R2, we have 2 amperes, and across R1, we have 1 amperes. So now that we know the currents and the voltages of this circuit, we can now then use them to calculate the voltages and the currents for this circuit. So let us do this. Let us draw a table. When we were using 56 volts, and when we were using 14 volts, so we now, so this will help us get the voltages when we have both cells for this circuit now. So we're using the voltages there that we got to get the voltages here. So let us now consider the other thing that is very important when you're using superposition method. We know that electrons will leave from the negative side. So here current will split according to Kirchhoff's. It will come back that direction and this direction. So what does this mean? This means that when we were using this P3, R1, because a resistor doesn't have polarity, right? But if you connect a resistor to the positive side, this is the positive side of the battery, the resistor would be more positive on that side. When our electrons flow from this direction and then they got there and then they got there, what happens is this one becomes negative. So and that side becomes positive. Again, the other thing that is important to note here on R3 is that if electrons took this direction and enter there, so this becomes negative and this becomes positive. The polarity is very important because it's what we're gonna use to determine the voltages for this circuit. So now let us write everything that we know on that circuit only on voltages. So what we know that on R1, when we're using 56 volts, our voltage was 48 volts across R1. Let's draw R1 here. So that is the voltage across R1. Sorry. So what is the polarity? Positive and negative. Let's draw R2 as R2 appears. So the volt drop across R2. What was it? It's 8 volts. Again, what is the polarity? Negative, positive. So let us draw a line here and draw a line there. So now let's come again to R3. So what was the volt drop across R3? It's 8 volts. 8 volts. But what was the polarity? Negative and positive. So once you understand this, you will be able to get this. If you don't understand this, then you will battle. We know electrons leave from this side, then here the current split or the electron flow split, and they join there. Sorry, I don't know what's happening to me. Now, what do we need to do? If we connect a resistor across this positive side, it will be more positive, and this one will be negative. Electrons come that side and that becomes negative. So this one positive, positive, but this one is negative. So now let us now go to that circuit. What is the volt drop? What is VR1 on that circuit? We figure VR1, we figure that VR1 is 8 volts. 8 volts, but what is the polarity? This side is negative and this side is positive. And then we come to VR2. VR2. Let's draw that resistor as it appears. And what is the polarity there? Negative and positive. And what is VR2? VR2 is 8 volts. So 8 volts, 8 volts. Okay. Let us now come to VR3. VR3, let's draw the resistor as it appears. So that's VR3, the polarity minus and positive. So what do we see here is the polarity for these resistors is not the same. Positive, negative. So when it's like this, it's gonna minus. If we had positive on this side, we needed positive on this side for us to add these voltages. So now that we have positive and negative, negative and positive, for us to get the voltage across resistor 1, when we are using both cells, we will have to save 48 minus 8, and this would be 40 volts. So now we know that VR1, when we're using both cells, is 40 volts. Now let us come to what is the polarity. We keep the polarity of the bigger one. Let us come to VR2. On VR2, the polarity is the same in the top and in the bottom. So what is going to happen here is we will add these voltages and we will get 16 volts. So what do we keep? We will keep the polarity as it appears for VR2. Let's come to VR3. VR3, the polarity is not the same. So what will happen here is, wow, what was VR3? It was 6 volts. So that was 6 volts So this 6 volts will be subtracted to 8. So my phone just rang, but I'll take that call later. So this is equal to 2 volts, right? Yeah, 2 volts. So VR3, we know that VR3 is 2 volts, and the polarity, we know that the polarity is gonna be the one of this. So we'll keep that polarity. So for this circuit, we know the voltages now. We know the voltages. Like here, we know that, okay, VR1, we know that the voltage across this one is 40 volts. And we know the voltage across VR2, which is 16 volts. And we know the voltage across VR3 is 2 volts. 2 volts. But we don't know the currents, right? So we need to calculate the currents now. So for us to calculate the currents, we need to consider the electron flow. So what was happening here when we still applied the same method that we've applied? So let us say by the time we used 56 volts, and also by the time when we used 14 volts, and when we have both cells, so the journey begins. So we said we want to consider the electron flow. So what was the flow in that circuit? On R1, it was on this direction, and on R2, it was on this direction. On R3, this direction. So let us draw these resistors here. I'd like to use this one. So a current across IR1. What was the electron flow direction? This direction. And what was the current? 6 amperes. R2, what was the electron flow direction? It was this direction. So what was IR2? IR2 was 2 amperes. Again, R3, what was the electron flow? This direction. And what was IR3? IR3 was 4 amperes. Let's come to this circuit when we're using the 14 volts battery, electron flow, that direction, and this direction across R1, and this direction across R3. So let us now draw R1. Let's draw R2. Let's again draw R3. So on R1, where is our R1? There, in the electron flow, this direction. What is IR1? We found out that it's 1 amperes. So let us now come here. What was the electron flow direction? On this one, R2, this direction. And what was the current across R2? Sorry, not R1. It was 2 amperes. So let us come again to R3. What was the current across IR3? It was 6 amperes. Sorry, not 6, it was 3 amperes. I'm taking the voltage. And what was the current flow? This direction. So again on current we do the very same thing. So the direction differs. So here we will have 6 minus 1, and this would be 5 amperes, and we will keep the electron flow of the bigger current. So we have electron flow, this current over IR1. So again we have said we have the same direction, so we'll have 2 plus 2, and we'll have 4 amperes, and we'll keep the electron flow on this direction over IR2. And we then have different directions. So here we'll have 4 minus 3, and this would be 1 amperes. So we will keep the electron flow on this direction, and this would be IR3. So now we know the currents. So we know almost everything. So here we know what did we figure? We figured that IR1 is 5 amperes, and IR2 is 4 amperes. So IR3 is 1A. But what we also saw is the current direction, that electrons will flow this direction. And here we saw that electrons will flow this direction. What did we saw across? Sorry, I'm making a mistake here. The electron flow across R1 is this direction, and the electron flow across R2 is this direction, and the electron flow across R3 is this direction. Oh, it's almost the same thing though. And what did we saw about the polarity? We saw that across R1 we are positive this side, we are negative this side, and we also saw that across R2 we are negative here and we are positive here, and we saw that across R3 we take that of the bigger one, so we are positive, negative, so we are positive and negative. So if you were to use this battery, you would assume that R3 is positive here, but that's not the case. I hope this video helped you and gave you full understanding of superposition theorem. On the next short video, I will be doing an exercise. Here I used an exercise to explain a lot of things. So in this video, I'll be dealing with what we are asked to cover to calculate on the exercise. Keep on the look for that video. Be on the look.